We've got 12 minutes, and I really want to introduce isostasy to you all today before we get out of here, and then we're going to go a little bit more into it later on over the next period or the next few periods. So, for our objectives today, I want you to be able to describe isostasy, isostatic rebound, isostatic equilibrium, and then we're going to discuss how the relationship between the function of isostasy relates to vertical plate tectonic motion and then vacancy diffusion. A lot of stuff. So for our pretest, since we don't have a lot of time, I just want everybody to raise your hand if you think that you could answer this in part or in full. So could anyone describe to me isostasy? Okay. So then isostatic rebound would be pretty hard. Do you think you could describe isostasy?
I know what that means. Yeah.
Okay, awesome. Excellent. So we got a little bit of groundwork. Excellent. Okay, could you give me an example of isostatic rebound?
Yes.
And then what does it mean to be in isostatic equilibrium? Is that something you think you might be able to answer?
Perhaps.
Okay. And then do you understand the relationship between isostasy and plate tectonics? A little bit? Good. Very good. But it's okay. If you don't have any idea, it's all right. We're going to go over it. Okay. So, first, the brain. We learn things, especially when we don't know we can't see the mantle. We can't see the inside of the earth. We are looking at like 4 miles to 23 miles down below our feet. So when we learn about how the interior of the earth looks, we associate it with other things that we know, and then our brain maps that out, and that's how we recall that information. And there's a couple of wires that people have a tendency to get crossed when we're talking about the mantle. So we're going to do this little activity. I just want you to grab the side of your head. I want you to pretend like you're peeling off the top of your head. I know it sounds funny. Then I want you to grab your brain, and I want you to set it next to you. Someplace safe, maybe on a piece of paper so it doesn't get dirty. Nobody poke each other's brains, that's just rude. Okay. So, now there are 3 activities on the table, 2 of which are review. They're important concepts to leading into how isostasy relates to plate tectonics. One of which is the slinkies, and I want you to go over again how P and S waves move and what kind of mediums they move through. And there are instructions on the pages. And then there's one with putty. You have some putty in front of you, and there is some instructions on what I want you to practice doing with the putty. And that is to get you thinking about how the mantle, as we discussed before, when you hit it really hard, it behaves like a solid, so it'll snap. And then when you move real slow, it moves a little bit more plastically. And then the third activity is the memory foam. And I want you to pretend like your hand is the crust, and then the memory foam is the mantle. And I want you to just squeeze it, press down on it, let go, see what happens, and write down your observations. And you'll have a few minutes to go ahead and work your way through some of those activities, and I'll walk around and answer any questions.
Yeah, those.
Oh, okay, I didn't see it.
So, you want to do the very best. So, you want to do the roll out. That's what the cut. The themes are to press it down.
So if you have, like, imagine 4 balls on the instruction. Push one this direction, so it's going to plug in to the one next to it, and now it's going to go that to where it's going to come over to this one. The next one, that is because it bunches everything together, and it's like that much follows you. It's some sort of if you hit the ball or like a earthquake, for example, you can have some sort of physical pressure applied to the human. And then an S wave is a shear wave. Picture really helps. So shear wave you have stronger bonds with solids. And so you're going to have your same 4 balls, and then there's going to be 4 balls that are spread out. And they're all attached, if you imagine, they're all attached by very strong bonds. So you're going to take that same substance, and then the bottom is going to move because it's attached to the top ones. And now it's going to drag that along. And you're going to get the bonds as you shift like this. And that's how you get the transverse structure.
So why is like this?
That's when it folds fast, it doesn't have
That's why it's like this.
Because when you pull it really fast,
Yeah, you're really
it's going to behave more like a solid. It's going to be like a solid system. Wait, if you hit a rock really hard with a number, it's great. That's kind of how I want you thinking about the putty in relationship to a noun. But then it takes some real slowly. It doesn't just break. It just stretches out. It's more ductile.
So I'm having trouble with what we're supposed to do with I mean, like this compression waves and transverse waves, right?
Yeah.
Is that what we're going for here?
Yep.
Okay.
Yep, and then just understanding why. When you're looking at like the structures and the material and the solid and the liquid.
Okay.
Why waves move through solid liquid and gases.
Okay, and the S waves are the transverse waves. Yes.
Did you get a chance to play with Putty?
Yes.
You guys all had a chance to play with the phone. Does everyone have a chance to play with the Putty on the phone or something? I need you all to redirect your attention back up here, and we're going to discuss a little bit why the activities are important and how they all tie together. Okay, so when we were playing with the waves, and I know some of this is new material, but it feels kind of new because it's been a long time, what did you notice from the paperwork and from the playing with the slinky? P waves, which are the compression waves, what kind of material will a P wave move through?
Solid liquid and gas.
A solid, liquid, and a gas. Good. And what kind of material will an S wave move through? What was that, Justin? I'm sorry.
Solid.
A solid? Excellent. Okay. So, the reason that's important is because from P and S waves, we know that an S wave will move through the mantle. And if an S wave can move through the mantle, then what would you assume that the mantle is made of? Or what state is the mantle in? Solid. But when we play with the putty, what did you notice when you were thinking about, okay, if I move it real fast, what happens to it? What happens to the putty? Breaks. Like a solid, like the S wave would move through a solid. So that makes sense. But then when you move it really slow, what does it do? Right. So if you apply some time and some pressure, it'll behave a little bit more like a plastic, but it's not a plastic. It'll behave a little bit like a liquid, but it's not a liquid. It's kind of like associating it with Jocelyn, for example. I'm picking on you because you participated so much. I'm sorry. Thank you. She is an education student. We are all education students. So like Jocelyn, we are education students. But John, for example, he has very different characteristics from Jocelyn. He is not Jocelyn. He is a man, for example. And not a woman. So, like, but not exactly. Okay. So, just a quick recap of what we already went over, and this is the velocity depth curves of a P and an S wave. And we can see here that when a P wave or an S wave travels through, it gets all the way to the end of the mantle, and then at the outer core, it stops moving. What would that tell us about the outer core? If an S wave can't travel through it, and an S wave can't travel through what kind of medium? Liquid. Right, then we would assume that it is a liquid, but the mantle then is a solid. Okay, so, real quick on the language, because we're learning some big stuff. The definition of isostasy is the process by which the Earth's crust adjusts. Forgive me, I have to backtrack. I forgot to get you guys to tell me what you observed about the foam we played with for the isostatic discussion. So what did we observe when the crust put pressure down on the mantle? It compresses. And then when you let it off, what happens? Comes back good. And they call that isostatic rebound. And then when it stops moving completely, either if you push it all the way down or if you've let it up, that's considered isostatic equilibrium because we don't have movement anymore. And some real world examples of that would be the Himalayas. The Himalayas are moving very slowly at 2 millimeters a year. And so there's pressure on the mantle, so it is not in isostatic equilibrium. However, the Rocky Mountains were made when the Phaleron plate subducted underneath the North American plate 65 million years ago, but that plate's no longer subducting. So would you think that that was in isostatic equilibrium? And for the most part it is. It's hard to get exactly equilibrium, but for all our intents and purposes it is. Okay, so the language of isostasy, the process by which the Earth's crust adjusts to loading and unloading by vertical motions. The prefixes, iso, meaning even or equal, and then the suffix is standing and stability. Can we think of anything that we've come across that has iso or a related suffix? So understanding iso, what would you think about that triangle? Okay, and then the isostatic phases would be, of course, an example is glaciation when you have a load on top of the crust, and then that load causes subsidence, and then when it melts, it slowly starts to rebound and it goes back into isostatic equilibrium. We kind of discussed some of the mantle characteristics, the plastic and the liquid. So what is it called if it is a solid but it has some liquid or plastic-like tendencies? They call it a solid state creep. Oh, thank you. So what does that mean? How does that happen? Okay, so what happens is in the atomic structure of the material, we have imperfections, and that there are vacancies within the atomic structure. So when a pressure is applied, a lot of pressure, like 4 miles to 23 miles worth of crustal material, what do you think will happen to those vacancies as the material presses down? And they call that vacancy diffusion. And this is why it's like a liquid, but it's not a liquid because only parts of it move at any particular time, and it doesn't move as a whole structure like you would expect with a liquid. Okay, so it's a lot of big ideas. I know. I'm so sorry. I threw all of that at you. But anyway, so can anyone tell me really fast if they could explain how isostasy relates to vertical tectonic motion?
Puts pressure on the mantle that reduces.
Yes. It does. That's exactly what it does. Thank you. Okay, you can all put your brains back in, but try not to forget that the mantle is very different from anything that you know. It's just kind of weird under such depths of temperatures. And then I forgot to change the pre-test to a post-test, but everybody has a post-test. And if at any moment you get a chance to fill it out, I would appreciate it because I am going to use this someday and in a future class, and I want to see whether you got some of the concepts that I was talking about. And if anyone has any questions, please feel free to email them to me, and I would be happy to discuss it in more detail. Okay, thank you.